Okay. So good morning, everyone, and welcome to the day 2 of the FDP. We are delighted again to welcome our dynamic speaker, Professor Rajiv Asthana, who will be presenting today on solidification processing. Over to you, sir.
Thank you, and good morning, everyone. Welcome back again to this topic, certification processing. So I'm going to look at a few things today with where I left off last time, that is yesterday. So yesterday I looked at these basic concepts in just sand casting, things about risers and screws and riser aids and those kind of things. Let us just finish up a few more things about practical aspects here. So when you make a simple sand casting or sand mold, we mix, as you know, we mix sand, a base sand with some clay and water. So the properties of molding sands are important because when you pour hot metal, there will be metal pressure and other things. So there are some data over here that give us the strength of green sand as a function of moisture content. And we see that there is an optimum range of water that is needed to get the correct strength in molding sand. Very low water will not give you enough strength, please.
This side next slide.
Here it is like this. No, it's not. I president is.
Okay, you want to keep it like that?
Yes.
Okay, all right. Can I get my laser pointer on it or no? I don't think so. Because the laser pointer, because, yeah, this one here. Okay. All right. Thank you. Thank you. So again, coming back to this here, the moisture content, the kind of sand, the shape and size of the grains of sand, all those things affect the strength of mold. The thermal properties of sands are also important. And at the bottom here, you're looking at a graph of thermal expansion of sands as a function of temperature. So as you see from these data, a silica sand has the highest expansion, followed by olivine, chromite, and zircon. Zircon sand has the lowest mold out of sands with low thermal expansion because then the stability of the mold is better. But again, the cost, the availability in those factors also determine what kind of sands should be used. Fluidity of metal is another factor to consider. And the standard test for fluidity is called the spiral fluidity test, where we have this kind of a standard spiral channel in a mold, and the metal is poured, and we measure the distance the metal flows before it stops flowing. So fluidity is not a scientific index, but it's a very practical parameter. It involves both rheological properties of the liquid and the thermal properties, the cooling and the flow behavior. So these empirical data on fluidity are shown for some metals here. Higher the superheat or higher the pouring temperature, higher is the fluidity. But then there is a challenge that higher temperatures also increase gas absorption from atmosphere. So there is a trade-off between how high temperature one can go to. And these are some data on solubility of aluminum. Solubility is plotted as a function of time. There is a sudden increase in the absorption of hydrogen. And then as the temperature of the melt increases or superheat increases, you have more gas absorption. By the way, for aluminum, hydrogen is the main problem, not oxygen, not nitrogen, because oxygen and nitrogen will form oxides and nitrites. Those are solid compounds. Hydrogen does not react, so it remains as a bubble in your solidified casting. So porosity forms mainly because of hydrogen dissolved in the metal, not nitrogen or oxygen. And the thing is that hydrogen, how do you remove hydrogen? Well, there are standard practices. Earlier, people used to use chlorine gas, bubble chlorine through molten metal, and then you remove hydrogen. But chlorine is toxic, so people started using hexachloroethane, tablets of this compound called hexa. They basically release chlorine. So right now, people have given up on chlorine, and argon is the main gas for use for degassing. And as we see here, that in industrial practice, the process called the Alcoa process, Aluminum Company of America, they use this kind of a cell, multiple cells in which aluminum is flowing from one side to the other, and this impeller has very fine pores from which argon gas is released. So as the metal flows in this chamber, it gets degassed. One common sense thing is that the metal should not be receiving heat while it's being degassed, because then you defeat the purpose of degassing. If you're pumping in heat in the metal while its temperature is rising, then it's absorbing more gas. So the standard procedure is to superheat the metal, turn the furnace off, degas. So there are a lot of practical considerations involved in metal casting, basic metal casting process. Let's shift gears. Let's look at some fundamentals here about structure formation in metal casting. So we know that most metals and alloys will form some sort of a grain structure. And when you do metallurgical polishing, grinding and polishing and etching, you are able to reveal the grain structure. We also know that the size of the grain is higher strength at room temperature as compared to coarse. For example, pour aluminum in a sand mold versus aluminum in a copper mold. The aluminum casting in the copper mold will be stronger because of finer grain structure. But again, you cannot change your production line from sand casting production line to permanent mold casting. So there are ways to get fine grains even in sand castings by inoculation in the methods. Anyway, so fundamentally, how do grains form? Well, if liquid metal cools, you have the process of nucleation, which means very teeny clusters of atoms form in the liquid metal. Some of those could melt back, but some will survive. And this is what the graph looks like for free energy for nucleus formation as a function of the size of the nucleus. So there is a competition between surface energy and the volume energy when a nucleus forms. And usually there is an energy barrier, which is shown over here. Once this barrier is crossed, nucleus is stable and will continue to grow to form grains. It also turns out that if you have a solid surface available inside the metal, then nucleation is easier, something called heterogeneous nucleation. And the solid surface provides an area where atoms can deposit and form nucleus. Once a stable nucleus is formed, grains will form by the process of growth. And here is the basic idea here. This is the solid metal, this is the liquid. As solidification takes place, this interface moves from left to right, more and more solid forms. But if you look at the temperature gradients, this is how the temperature gradient looks in solid and in the liquid. The liquid is super cooled in front of the interface. So what happens is if you have initially a planar front, it moves into the supercooled liquid and a perturbation forms. This kind of a protrusion forms and it can grow and then it can shoot side branches to create what is called a dendritic structure. So we have dendrites forming during cooling of the metal. So depending on the temperature gradient in front of the interface and depending rate, we can have different kinds of grain structure. We can have a planar front solidification, cellular structure, cellular dendritic, convex dendritic, and then equiaxed structure. So these are the critical parameters, temperature gradient and the cooling rate. They determine the kind of structure that we get. So temperature reached begin to stack together, and as cooling continues, which means as latent heat gets released, we have all cells stacking like this. Eventually, when everything is solidified, we get these kind of unit cells in different areas of the casting. So this is one grain. This is another neighboring grain. So inside each grain, the unit cells are stacked at one orientation. In the neighboring grain, you have the same unit cells at a different angle, and so forth. And the boundaries between those is grain boundaries. So on a macroscopic scale, this is what the dendritic structure looks like. And inside the grain, as you can see in this picture here, inside each grain, you have dendrites. And we also know that these dendritic structure is very similar to ice crystals. When water solidifies to form ice, we have exactly the same kind of crystal patterns forming. So what is the importance of studying this kind of a behavior? Why do we want to study dendrites and grains and all of that? The reason is that those features are related to mechanical properties of your casting. So here we are looking at that rate. As cooling rate increases, grain size becomes finer. But the problem is that there is a lot of scatter in the data. The correlation coefficient is not very high. It's about 0.81 for this particular example. So a better way to characterize the structure is in terms of the dendrite arm space. Really, if you look at the dendrite arm spacing, this is what happens to tensile strength, yield strength, and elongation. In these graphs on the horizontal axis, x-axis, we are plotting 1 over square root of dendrite arm spacing. It is lambda to the power negative 0.5. So it is so from left to right, the dendrite arm spacing is decreasing really. And that's why the tensile strength is growing up, yield strength is going up, even inductility goes up a little bit. So this is how we relate useful practical properties to structure that forms in castings. But as I said, it's easier to characterize. The grain structure. So quite often people measure the grain size and then try to relate it to mechanical properties. So this is an example of a coarse grain structure. This is a finer grain structure. And it turns out that if you plot the yield strength of your casting as a function of 1 over square root of the grain size, you get a very nice linear correlation, something that is called the Hall-Petch equation. The yield strength of the casting varies as inverse of the square root of the grain size, average grain size. So a lot of alloys and metals show this kind of a Hall-Petch behavior. When you get into nanometer size scale, things could be very different. So Hall-Petch may not apply, but for common industrial purposes, Hall-Petch equation is very useful to relate mechanical properties like yield strength to average grain size. And how do we modify grain size? How you make grains fine? Well, there are many methods available. One is, of course, the cooling rate. Faster the cooling rate in your mold, finer the grain size. But then people also use other methods to refine the grain structure. For example, for aluminum, people use titanium or titanium diboride inoculant to refine the grain structure. In smaller castings, people use high frequency vibrations. Solidifies into solid, you apply an ultrasound, and that will mechanically break up or disintegrate grains. When sound waves propagate through a liquid, they create cavitation, which is basically formation and implosion of very fine gas bubbles. And that process of implosion creates huge accelerations locally or huge forces that can break up crystals. So that's a mechanical method of refining the grains. And then you can also make grains fine by using high pressure. Like in squeeze casting, when the metal solidifies under very high pressures, grain structures become fine because of large undercooling and also because of very good thermal contact under pressure, contact between the mold or the die and the casting. So there are different ways to get fine grain structures to get high mechanical properties. Over here, we are looking at a graph and actual data, some actual data on the relative wear of a brake rotor of a vehicle cast in a sand mold and in a permanent mold. So this curve is for sand casting, the lower one is for permanent mold casting. The same rotor, brake rotor, was cast in two types of molds, and we are measuring the amount of wear in micrometers. And this rotor was running against a counter face, and the contact pressure was about 5 newtons, and RPM was 400 revolutions per minute. So under these conditions, we are measuring how much was the wear of the rotor as a function of time of running. And what we see here is that after running for a fixed amount of time, the sand cast rotor wears out more as compared to the permanent mold cast rotor. And that is basically because in a permanent mold casting, you get finer grain structure, higher strength, and therefore less wear. By the properties of casting by changing the morphology. So we use a treatment called modification treatment that is used to change the eutectic silicon in aluminum silicon alloys from plate-like appearance to more globular structure. So in aluminum silicon alloys, normally we add a very small amount of sodium or phosphorus or strontium during melting and casting. And those elements basically change the shape of silicon from plate-like to more globular. And people have done a lot of fundamental research. What really happens when you add these elements? Why does silicon become more rounded? The basic concept there is that these elements, sodium or phosphorus, strontium, they poison the growth along the length of the silicon crystal. If silicon cannot grow horizontally in two directions, it can only go sideways. And that's why you get a more rounded features. Well, what is the benefit here? Without any treatment, you get about 124 megapascal tensile strength and 2% elongation. Tell us expendable is something where every time you have to make a new mold to make a new casting. So like sand casting processes will be expendable, but die casting will be a multiple use mold process. So how do we make a simple sand mold? Most often we use a match plate, which is basically a metal plate or a wooden plate pattern, and the rising and gating system already mounted. You put the mash plate between the coping, put sand and clay and water mixture on one side. The whole thing is vibrated, and then you can use a squeeze and jolt machine. And then this compressor or platen will press down the sand. Once one side is done, you flip it down and repeat these steps to make the other half of the mold. When both sides are done, you can open the mold, remove the mash plate, put any sand ports if you need to make any internal surfaces, and then reassemble the mold, pour hot metal, and once the casting solidifies, you get your final part. Weight on the top, especially if you're pouring heavy metals like iron or steel and all, the coke might float up. So that's the standard procedure, and only about 50 to 60% metal ends up in the actual part. The rest of the metal goes in scrap and risers and gates and runners and those kind of things. But it's a cheap process, quite inexpensive and easier to apply. Another process is the vacuum molding process or the V process. And here we don't have to use any to use a match plate with vent holes in it. and that mash plate is placed over a plate that is hollow, and you can pull a vacuum through that. So in the next step, we put a plastic film, like a Teflon film, warm it a little bit so it becomes flexible, and then drape the pattern with the flexible Teflon film. Now you start to pull the vacuum through this bottom plate. When a vacuum is pulled, the plastic will tightly cover the pattern because you have the vent holes in the pattern. Next, you put the flask, one half of the flask over the pattern, and pour sand, just loose, unbonded sand without any clay and water. This may have to be vibrated a little bit so sand settles in all areas. Then you put another plastic film on the top. In the next step, you start to pull the vacuum through the flask and release the vacuum in the bottom plate. So when you do that, you are able to separate this. So this is one half of the mold that is ready. You repeat the same step with the second half, with the rag half, and make the matching halves. Put the two together, pour hot metal. And so in this kind of a process, there is no shake out needed. Normally in green sand casting, you have to break the mold to recover the casting. Here, once you release the vacuum, the whole thing comes out released for milling sand. So in that sense, it is a pretty neat process. But in terms of the yield, it's not a very high yield process. The yield is about the same as the green sand casting process. Two other processes that utilize sand are sodium silicate CO2 process and then resin bonded sand molding, also called shell molding process. In the sodium silicate CO2 process, we use a base sand mixed with sodium silicate, which is popularly called water glass. About 3 to 4% water glass is added to a base sand, olivine or silica or zircon or one of those sands. So that then you ram up a mold, tap the sand around the pattern, and expose the sand to carbon dioxide. To do that, you can either poke holes or vents in the sand mold, or you can use a pattern which has holes or vents. So very close to this pattern, you will have a strong shell of silica and base sand form. So, and you can use this backing sand that can be reused to make more molds. In the resin bonded sand molding process, also called shell molding, we use resin, not a thermoplastic, but a thermosetting resin. So thermosetting binder or resin is mixed with the base sand, and it is brought in contact with a hot metal pattern. So this is the hot pattern, like a mash plate that is heated to about 150 to 230 Celsius. So this is the sand mixed with resin. This is the hot pattern. You invert the mold so that the sand comes in contact with the hot pattern. And the thermosetting resin and to the pattern. Once a sufficient thickness of shell is formed, depending on the metastatic pressure that would be needed, once you get the thickness, invert the mold and remove or drop any unused sand here. Then this shell is stripped or separated from the pattern. A matching half is made, and then the two halves are assembled together. Put some backing shot, steel shot or sand, and pour hot metal. So in this process, as you can see, when hot metal is poured, the resin burns out. Just finish here, and very tight tolerances. There is no water. There is no moisture related defects like porosity. So the process is cleaner and it gives you better quality finish. So all of those. Another sand-based process is the so-called lost foam process, or sometimes called the evaporative pattern casting process, depending on the patent. Different people make some changes and you have a slightly different process, but the basic concept is pretty straightforward. We use styrofoam pattern to make our parts. So the first step obviously is to create foam pattern, and that is done by injecting styrofoam beads in a hot dye. So the beads will fuse together and form the foam pattern. Then the foam pattern is placed or covered in loose unbonded sand. And before that, you will have to attach runners and gates and risers. They are also made of foam, and they are attached by just simple hot glue or by putting some pins. So when the whole thing is assembled, you cover this in sand and pour hot metal. The foam burns out, the metal takes its place. The interesting thing is that as foam burns, it does not cave in. The liquid metal keeps sand from caving in and causing defects. Sometimes people also apply a ceramic coating, like a thin wash, before putting the pattern in the sand. That is just to give you better finish. So the surface texture of the pattern is important. If the styrofoam beads are not fully fused together, then you get a rough texture. If they are overheated, again, you get a poor texture. But if you get the right temperature, then sometimes vacuum is used to suck the gases, burnt foam from the mold. And flexibility, you can make fairly complex parts like cylinder heads and pistons and everything. A lot of small engine manufacturers use this process. One disadvantage is that the pattern is wasted. There is no way to but you don't need a draft angle or on your pattern. Normally in a sand casting process, when we use wood pattern or metal pattern, we have to have some draft or taper so that the pattern can be taken out before the metal is poured. Here, we don't need to machine a taper because the foam burns out. There is no shakeout needed. And it's also a useful process for castings where weight of the pattern could be a concern. I mean, just imagine you're trying to make a large casting using a metal pattern to ram up a mold. The weight of the pattern could locally deform your packed sand. But if you're using foam, foam is so light that there is no danger of any deformation of your sand. So, process, centrifugal casting process. Here we use, as the name tells you, we use a rotating mold in which the metal in different orientation. In a vertical orientation, where you have the mold spinning in this kind of a plane, and the metal is poured in the spinning mold, or you can have a rotation in the horizontal. So the axis of rotation here is horizontal. The metal is poured. You make a cast. So this process is used to make some special shapes. Mostly these kind of hollow tubular parts, gear blanks, pressure vessels, propeller hubs. Those kind of things are most easily cast using centrifugal casting. I mean, if you make this kind of a part, like a pipe like this, without rotation, how would you do that? In a sand mold, you will have to make core, a sand core, put the sand core inside and pour metal around it. But when you use centrifugal casting, you don't need any sand core. The centrifugal force itself takes care of that problem. And people use this approach for many creative things. For example, you can make castings of different layers. For example, you can pour steel first, get a certain thickness with steel shell. Then pour copper or nickel egg-share composite with different layers of different metals. And that could be beneficial if you are thinking about gradual change in the properties from one side to the other, thermal expansion or conductivity or other things. So that flexibility is possible. And people use this approach to make lighter than aluminum. So all the graphite is going to segregate closest to the axis of rotation. In other words, all the graphite will segregate on the inside circumference of this kind of a bearing. So you'll get a very low friction on the inside surface. And essentially you have created a bearing material. So a lot of different creative things people have done using this approach. You can also add high powders to aluminum by stir casting, and you pour that mixture or slurry in a rotating mold. Carbide is heavier than aluminum, so it will segregate on the outer surface, and aluminum will be on the inner surface. So you can create an extra hard exterior. All different kinds of creative things people try out. Investment casting or the lost west casting is a very popular process with many different industries. It is also used by artists and jewelers, jewelry making. And as we all probably know, this is one of the most ancient processes. It's been used for over 2,000 or 3,000 years in a more primitive form. But in a more modern form, this is how the process works. We use wax patterns to make castings. So first you melt and inject wax in a die to make a wax pattern. Then many wax patterns are connected to a wax shaft. So you create a tree or clusters of many patterns mounted on one single wax shaft. Then you go through these steps, stucco coating, which means you dip this wax cluster in a slurry that contains very fine ceramic powders. So dip it in, take it out, get a coat of ceramic. Now, by the way, it's a water-based slurry, but water will not spread on wax. So you have to add some surfactant, some chemicals so that you get a uniform film of fine ceramics on the wax. So dip it once, take it out, and immediately dip the wet cluster in the second tank where you have coarse ceramic powders. So when you dip it and take it out, you get a secondary or backing layer of coarse powders. Then you hang this cluster in a room with controlled humidity and temperature, let it dry out. It may take many hours. Then you go for a second step, dip, dip, dry. Again, come back, dip, dip, and dry. So typically it takes almost 3 days to get about 1/8 of an inch thick ceramic shell over your wax pattern. That is the standard procedure. Many years ago, I had a student, undergraduate student, he used electrophoretic deposition to form ceramic coatings on wax clusters. We know that electrophoresis is a process where we use charged particles to deposit on a surface. So he tried the same thing on wax. Now, wax is not an electrical conductor, so you cannot make an electrode out of wax. Better powder to wax. So if you have this kind of a conductive wax pattern, then you can use it as an electrode in an electrophoretic that he could deposit on wax that typically takes into 4 days to build up. So that was an interesting demonstration, but of course, before a process can be implemented, it has to be staged. So I think this process does not use the electrophoresis yet, industry, but what is done next here is that the shell is heated, wax is melted out to get the hollow shell, and the ceramic shell is then sintered at high temperatures to get strength. Once the shell is strong enough, you pour hot metal and you get to casting. So some of the steps can be automated, like dipping steps here can be automated using a robotic arm. And once the shell is made, you don't need any sand or anything to support it. You just make it stand on some kind of a support and pour hot metal to make the casting. Once the casting is solidified, you have to break the shell to get to casting. So the wax that was melted is reused to make more wax patterns. The broken ceramic shell for investment is not used in foundry practice, but I believe it is used in some construction work. It can be reused to a certain extent. So this process is pretty. Of course, you have to of the metal and shrinkage of the wax. When you design your pattern and you want to get the final casting, you have to add the shrinkage of wax and shrinkage of metal in your pattern design. And it is used widely to make turbine wheels and blades, body implants, titanium airframe parts, jewelry, precision machine tools, and also some medical implements or tools. So this process, to my knowledge, is still not very popular with automotive industry because there are many intermediate steps involved. And automotive people, they want very fast, rapid production. So they prefer die casting or that kind of a process. But then die casting is not normally used with iron. You don't die cast ferrous alloys. But this process can make ferrous castings also. But for automotive people, instead of die casting for ferrous alloys, they can use a powder metallurgy process. So that we'll see later on. Sure. Okay, maybe I have another 15 minutes or so.
Yeah.
Okay, I'll just finish that one quickly. Permanent mold casting. So now we're looking at multiple use mold processes. And as we know, in permanent mold, we use a die, not sand, to make a mold. A die material could be cast iron or steel, copper. Sometimes graphite dies are also used. Graphite is pretty easy to machine. So you can make the part, cavity and risers and runners, everything inside the die. Usually we make split molds in multiple halves. So in this example, we're looking at a 2-part die. You assemble the die, pour hot metal. When the metal solidifies, you get your casting. So this die can be used multiple times. Typically to few hundred to over 250,000 parts can be made using the same set of dies. So die life is pretty long, and it can be further increased by applying some refractory wash or coating to reduce hot corrosion when hot metal is poured. So a lot of different things can be done to increase the life of the die. One can also put sand core in a permanent mold, like in this case, these are the sand cores placed inside the die cavity. You can have multiple cavities, molds to increase the rate of production. And typically you mount many permanent molds on a rotating platform like this, and each mold goes below a pouring station, gets the metal, and that's how the process works. So it's a pretty quick process because cooling time is faster. Casting yield is similar to sand casting, 50 to 60%, because you still need risers and gates and runners. But there are no moisture related defects. Unlike green sand casting, here we don't have any water to cause porosity or other kind of problems. Two variations of permanent mold casting utilize low pressure permanent mold casting and vacuum permanent mold casting. So on this side, left side, we are looking at the low pressure permanent mold casting. The idea here is to use pressure of a gas to make the liquid rise into the mold cavity. So this is a pressure chamber inside which we have a crucible, and the heater is also inside the furnace. So the solid metal is heated. Once it is melted, you lower this feed tube in the molten metal, and the feed tube is connected to the permanent mold. So this is the mold cavity here that is connected with the metal using the ceramic feed tube. So this is the pressure chamber. Once this is all set up, the temperature is correct, you introduce a gas. Air is normally not used, even though it is shown air here. Argon is used to reduce contamination in the surface. So as argon pressure builds up, the metal will gradually rise through the tube and fill up the mold cavity. You can release the plunger to allow air to escape as the mold gets filled. So what is the advantage here? Well, in the traditional process, you pour metal in the die. So gravity pouring is used here. This process, in this case, as compared to gravity pouring. So that's one advantage. Yeah, I remember many years ago in the early 90s, maybe about 40 years ago or so at NASA, I was using this process to make some composites. So what we were doing was slightly different. What we had was, I'm telling this because I learned a lesson based on something that went wrong. And what happened was we were trying to make some composites. So in this tube, we had some sapphires. We could put this fiber like this in contact with the molten nickel. And then I would pressurize the chamber and allow the metal to rise through the fiber bundle under pressure. And once I had many sensors, so I could track the movement of the metal. So once the desired height was reached, I would raise the tube above the metal and let it cool. What happened was something interesting. I was running this process and I was building up pressure, but my sensors in this tube were not registering the rise of the metal. This is a black box, so you cannot see what is happening inside. So we have to abort this. We opened this furnace or pressure chamber. What we saw was this. There was a superalloy had flowed out and filled up this region here. And this aluminum crucible floated up and jammed against the bottom of this tube. And there is no from that example. Anyway, so this is how we use low pressure of gas to control the rate of filling. The same thing can be done using a vacuum. Instead of positive gas pressure, we use negative pressure. So in the permanent mold, we use these vent holes to pull a vacuum and allow the metal to rise and fill the mold cavity. So because you're using a vacuum system, the process is even cleaner as compared to this kind of a process. Squeeze casting uses high pressure. It's like forging. Instead of forging a solid piece, you're forging liquid metal. So metal is poured in a die, metal die that's water cooled. The die is closed, pressurized. When the metal solidifies, you open the die, get your casting. Very simple process. But the main advantage here is that because of high pressure, the thermal contact between the die and the metal is very good. And therefore, heat transfer is very rapid. The second reason is that because of high pressure, the metal has very large supercooling or undercooling, which means the solidification temperature decreases substantially. You have a lot more supercooling, which means a lot more nuclei will form and you can get finer grain structure. So because of good thermal contact with the die and because of supercooling, high supercooling, you get very good quality castings from here. You don't need any risers or gates because pressure, when you apply pressure, you don't need risers. So the yield is close to 100%. And high precision parts are made and you don't need very high fluidity also because pressure compensates for fluidity of the metal. Now this process is a little bit different than die casting. And I think that is probably the last process I'm going to look at. Then we can stop. Maybe just one more slide after that. So what is the difference between die casting and squeeze casting? Well, the main difference is that in the die casting, we inject the metal under pressure. That is not done in squeeze casting. Squeeze casting, we just pour and pressurize. But in die casting, we inject the metal, and when the metal is filled up in the die, we maintain the pressure. The problem with die casting sometimes is that the injection in your casting. So sometimes die cast, they are not going to die. So what is which means to bring the temperature of your alloy between the liquid and solid or waxy material and put this because this is more viscous. There will be very little turbulence when the die cavity gets filled for the liquid. So semi-solid die casting is used to make parts with better quality than traditional die casting. And as you know, die casting is mostly used for making thin-walled components. because they will be difficult to produce by gravity casting in a permanent mold. Gravity may not give enough pressure to fill small sections. But with die casting, you can fill thin sections to make them wall items. So that's a very commonly used process for automotive industry. Well, single crystal castings, maybe I'll just skip it, but we saw that we make turbine blades, single crystal turbine blades using special casting processes. We also can make silicon or germanium or other semiconducting crystals using the approach called Czochralski's crystal pulling process. And the interesting thing is you can make these kind of crystals that are 5 to 6 feet long. One single grain of a metal that is really long. And these kind of precision cut to create single crystal silicon wafers, and they are used to make integrated circuit chips by depositing circuitry and all that. So these are some special processes. So I believe my time is up. So we will not get into more details here. And I can stop here. If anyone has any questions or comments, feel free to make those.
We will be having one single grain of.
Yeah, you have one single grain.
We will be having one single grain.
Yeah, there is no grain.
One grain.
So